So we know that the work done on an object will transfer energy to the object. How much energy? It will transfer the same amount of energy as the work done. So if 100 joules of work were done to an object, that object's energy changes by 100 joules. Now, if the work done on that object causes the object to move, the object now has kinetic energy or moving energy. But if the work done on the object is not causing the object to move, the object may have stored that energy. And that stored energy is called potential energy. The object isn't moving or doing any work, but it now has the potential to do so. Now there's various forms of potential energy and different kinds of energy described to you in section 5.3 of your textbook, so I would encourage you to read about that. And while there are many forms of energy, what we're going to concentrate on for this class is gravitational potential energy. And this is the energy that an object has due to its height above a surface. So it's the energy an object has due to its height above a surface. So we say it's capital E for energy, a subscript G for gravitational potential energy equals m times G times H. So what are all these pieces? Well, we know energy is measured in joules. Lowercase m is mass measured in kilograms. Lowercase g here, that lowercase g is an acceleration value. It's the acceleration due to the force of gravity. So like any other acceleration, its units are in meters per second squared. And finally, the h is your height. So the height above a surface, and that's measured in meters. Remember that 1 joule must equal 1 kilogram times a meter squared over second squared. So if you look at the units on this side, and you can work it out, you'll end up with kilograms times meters, so that's meters squared over second squared. So the units do work out. Let's look at an example of this. Let's say that work was done to lift the book from the ground to the top of the desk. So we're doing work, we lift the book from the ground to the top of the desk. Exactly how much work was done? Well, we would have needed a force that was equal to the gravitational force. Force is mass times acceleration, so the gravitational force is mass times gravitational acceleration, m times g. And we use that force to move the book over a certain distance. How much distance? We move the book a distance of whatever the height is of the desk. Now we know the formula for work is force times distance. If work is force times distance, force is mg, distance is h, then the amount of work done on the object was m times g times h. M times g times h, well, that sounds an awful lot like the amount of potential energy an object has due to its height above a surface. So we did work on an object, and that changed the object's energy. How much work did we do? We did m times g times h amount of work on an object, and that's why the object now has a potential energy equivalent to m times g times h. Let's look at some numbers here. Let's say the desk has a height of 1.5 meters. So it's 1.5 meters tall, the desk has a height of 1.5 meters, or that's the height that the book is now at when it's on top of the desk. And let's say that book has a mass of 0.15 kilograms. What then would the book's potential energy be relative to the ground? So you're looking from the height of the desk all the way to the ground, which again was the height of 1.5 meters. We have a formula for potential energy. Potential energy, or gravitational potential energy in particular, equals m times g times h. The mass in kilograms is 0.15 kilograms. G, and you'll get to memorize this pretty soon, is 9.81 meters per second squared. That's on the surface of the Earth. And I would think it's a fair assumption that we're on Earth, so the gravitational acceleration is 9.81 in that case. And the h, the height, as we said, was 1.5 meters. We multiply all that together, 0.15 times 9.81 times 1.5, and we'll get 2.20725, and that's units of energy. That would be joules. And if we're looking at significant digits, our data has 1, 2 sig digs. So we should only have 2 sig digs. So we should have 2.2 joules of stored energy in that book. And just so I can be very clear, g, which equals acceleration of an object due to gravity, that equals 9.81 meters per second squared on Earth. 9.81. Now note, potential energy is measured relative to a surface, be it a desk or the top of the ground. Your height is always relative to some surface. Let's look at this example so I can really explicitly say what I mean. Let's say the book is raised further to a height of 1.0 meters above the desk. So we're going to lift the book up even further, and the book just stays there. Say we're holding it. Now, what's the book's potential energy relative to the desk? And then what's the book's potential energy relative to the ground? Well, we have a formula for potential energy. Gravitational potential energy equals m times g times h. Gravitational potential energy equals m times g times h. Okay, well, the mass of the book is the same, and we had mass equaling 0.15 kilograms. So m is the 0.15 kilograms, and it's the same for both A and B because we're dealing with the same book. Its mass didn't change. We're on Earth, so g is 9.81 meters per second squared. 9.81 meters per second squared. But what about the height? Okay, now the height in part A says, what's the height of the book relative to the desk? So where the book is to where the desktop is, that height is 1 meter, or 1.0 meters. So that's the height we'll put in for part A. But for part B, we're looking at where the book is relative to the ground. So what's the height from where the book is all the way to the ground? Well, it's the 1.5 meters that takes you up to the desk, 1.5, plus another 1 meter to get you above the desk, 1 meter there. So you add those two, your total height is 2.5 meters, and that's the number you'll put there. So for part A, the book's potential energy relative to the desk equals 1.5 joules. That's rounded to 2 sig digs. And rounded to 2 sig digs, the potential energy relative to the ground is 3.7 joules. If you feel comfortable with this, go ahead and look at some homework on page 212, the practice problems there, numbers 41 to 49. If you need more help with this, with that, I'm going to make a video going over those questions. All right, thank you.